All right, we got one more example of a confidence interval here for proportions. So insurance companies are interested in knowing the population percent of drivers who always buckle up before riding in a car. They randomly survey 387 drivers and find that 292 claim to always buckle up. Construct an 88% confidence interval for the population proportion that claim to always buckle up. So once again, we don't know the proportion of drivers who say they always buckle up, so that's an unknown quantity, P. But it is the mean or the center of the sampling distribution. So this would be a representation of the sampling distribution. We have a sample for which the proportion is 292 out of 387, and that gives it a proportion of 0.0 or 0.7545. So roughly 75% of this population always buckles up, or I should say roughly 75% of the sample always buckles up, and that's our best estimate of the population proportion of people that always buckles up. But that estimate is a point estimate, and it has no confidence. In order to increase our confidence in this estimate, we have to increase it to an interval of numbers. And in order to do that, we take into consideration the fact that we're in the sampling distribution and we know the spread. So the spread of the sampling distribution is the standard error. Now, we don't know how to calculate, we don't have enough information to calculate the exact standard error because we don't know P. And the standard error of the P hats is equal to P times 1 minus P over N. But we do have an approximation for P, so we're going to use that approximation instead to get an approximate standard error. So if we use that approximate standard error, what we want to do is we want to extend above and below our point estimate so that we can capture 88% of all the sample proportions in the sampling distribution. So we're trying to make sure that we extend far enough above and below with the margin of error that we're going to capture 88% of all the sample proportions. All right, well, the standard error is actually 0.0219. And to find the margin of error, which tells me how far to extend up and down from the point estimate, to find that margin of error, I need to know Z star, and I need to know the standard error of the P hats, which I have an estimate for the standard error, 0.0219, and I just need to find out what the Z star is. That's the value that's going to separate the region here that we're looking at, the Z score that separates up here and down here. All right, so to find that Z score, what I'm going to do is I'm going to look at the fact that 6% of the area is below that 88% in the middle, and 6% is above. So if I'm trying to calculate that Z score, I'm either going to calculate the 6th percentile of the Z distribution, but that would be negative, so I'd have to take the absolute value, or I could just capture the 94th percentile, which would be this 88 plus this 6 to take me all the way up to here. The 94th percentile would be positive, so I could just use that number directly. So I have two choices. I either capture the 6th percentile, which is the percentage below the 88 in the middle, or I could capture the 94th percentile, which is this 88% plus this 6% to make 94% right here. If I do the 6th percentile, though, it's going to give me a negative number because that's below the population proportion, and it's going to I'm going to have to actually take the absolute value of that instead of taking the exact number. So I'm just going to go ahead and do the 94th percentile so I don't have to worry about that. So to find the 94th percentile, I'm going to use Python scipy.stats. So I'm going to import scipy.stats as stats. Then I'm going to use stats.norm, which is the normal distribution, but I'm going to use the PPF, which is the inverse normal. If I give it the area to the left, it'll tell me the Z-score with that area to the left. So the area to the left of this Z-score right here, that area to the left is a total of 0.94. And then I do that, I run that in Python, it gives me this number. This is my Z star. This is my Z star. So that's the number I need up here, Z star. So my margin of error then is that z star, I'm going to round it to 1.55, multiplied by my standard error, which I found down here. When I do that product, I find the margin of error, which is roughly 3%. So from my point estimate, 75%, if I go up or down roughly 3%, I'll create a confidence interval that 88% of the time would actually capture the true population proportion. So if I follow this process 100 times, I would expect 88 of those times I would create an interval that actually captured the population proportion. So pretty much I do that. The population proportion is somewhere between the lower bound, which is the point estimate p hat minus the margin of error, and the upper bound, which is the point estimate p hat plus the margin of error. So p hat is smack dab in the middle of a confidence interval for p, or sorry, yeah. So let's see. That gives us these two numbers. So this is my confidence interval. I have a confidence interval here from 72% to 78%. So I'm 88% confident that my confidence interval between 72 and 78 captures the true population proportion.